most of the time, even in Algebra 2, when we covered this stuff, we kind of just launch right into arithmetic and geometric sequences and series. Even in Algebra 2, there was a section before that which covered some of the basics of this that was not covered. And we're going to do it this time, mostly for some things that I think don't usually come up so much in Algebra 2, but they come up more in this class and pre-cal, that maybe it would help if we saw it a little bit here and didn't just expect that later you were, comfortable with it. So, right, so the first thing, again, this is sequences and series. So the first thing is to define a sequence. And you can see this is the textbook definition of it. Other ways I've seen it presented is an ordered list of numbers, usually separated by commas. Now, the ordered list part of it, you can see those lists of numbers, and you can see they're separated by commas. Right? What makes them ordered is you can see that every one of these has got a subscript. Like A1 means the first term in the sequence. A2 means the second term in the sequence, right? And so on, right? They're in order. Now, the way the book is describing it here, they're saying this is like a function, right? And we know what a function is, right? A function is something where you have an expression on the other side that involves x. If you want to know what the value of the function is, you plug in a value for x and you calculate. Okay. For a sequence, you don't use f of x, you use a sub n. And the expression that we're going to use on the other side has got an n in it. And the way you find the value of a sub n is you plug in a value for n. Now, n can only be counting numbers. For the most part, is only counting numbers, meaning n has to be 1, 2, 3, 4, like that. There's not decimal values, there's not fractions, there's not negative numbers, right? N equals counting numbers. So whereas for a function, you can plug in any real number unless there's some domain problem like with a logarithm. For a sequence, you're only plugging in these counting numbers. Okay, the last, let's see, what other that? So these are the terms, right? Each one of these, this A, A1, A2, A3, those are the terms of the sequence. And if you see these dots at the end, right, that means it keeps going on forever, and that would be infinite, right? And then as they're saying here, if it only includes so many, a finite number of terms, then it's called a finite sequence. Good. Get up now. Okay, so if you're given a formula for the nth term of a sequence, that would be this here. A sub n equals, and on the right, we've got an expression and let's just call it the independent variable is n. That's what you're going to be able to plug in. If you're going to find the first, this one says find the first 4 terms of the sequence, that means you want to plug in n equals 1, n equals 2, n equals 3, n equals 4. And just calculate. And if you recognize patterns, because you've done this before, that's all right. But it's just this first section is not about those patterns yet. Okay, we're not interested in the fact that that's an arithmetic sequence, and we can tell because it keeps going up by a common difference. Right? We'll get to that in the next section. Good, Hannah. Okay, here's one where notice that here's the formula for the nth term of a sequence, and this time the n is an exponent. We're just going to make it do some different things, right? When I plug in the n equals 1, then that's the exponent of -1. Since -1 to the first power is -1, you're subtracting 1. But when n equals 2, now you're raising -1 to the second power, which is going to make it +1, and you get 4, because you're adding. When n equals 3, it goes back to a subtract, because -1 to the odd power is going to be -1. So back to 2, and when n equals 4, it's back to 4. So you just see the pattern there. I'll just say that all these are just right out of the book. Okay, here's one where the terms themselves are going to alternate signs. Again, because in the numerator, you've got -1 raised to the n power. So every time you increment n by 1, then it's going to flip the sign. So it still has another n in the denominator, but still for n equals 1, you're going to plug in 1 in both places, here and here. You can see the progression as n equals 1, 2, 3, and 4. The denominators are going up, right? 3, 5, 7, and 9. The numerators are alternating between -1 when -1 is raised to an odd power and +1 when it's raised to an even power. So you get negative, positive, negative, positive. So if you want to create a sequence and have it flip signs, that's how you do it. Put a -1 raised to the power. Good. Okay. Write an expression for the apparent nth term of the sequence for each sequence. And this is a little bit of guesswork that we wouldn't have to do in the next lesson, because when you see the pattern, we've got a way to figure out the formula. But this, they're just expecting you to try to figure out if you could see the pattern and see how you could represent it with an expression which has n in it. So for the letter A, you notice the pattern, right? When n equals 1, they've done the same thing here. Here's the terms of the sequence: 1, 3, 5, 7, and that's for the first term, the second term, the third term, the fourth term, etc. So we're trying to come up with the relationship, some kind of a formula, right? A sub n is an expression that has n in it, that when you plug in 1, you get 1. When you plug in 2, you get 3. When you plug in 3, you get 5. And it's somewhat of just playing with it. I mean, even if I didn't have it written there, I would be thinking, well, what happens if I double it? Well, then I would have n equals 2. Okay, what if I said n 2 times that minus 1? 2 times 1 minus 1 would be that. 2 times 2 minus 1 is 3. 2 times 3 minus 1, 5. You just kind of play with it, trial and error kind of thing. And they end up getting that formula exactly. I mean, there's not a way to look at every pattern and say, this is exactly how you're going to find every pattern. No, some you just have to look at. And we really don't do much of that. We're just looking at it more generally in this section, and then next section we'll figure out that actually we've got a way for this kind of a sequence to find that. Now the next one, when we do it on the next slide, just notice that what we're aiming for here has got opposite sign. Each term has the opposite sign from the previous term. So how are we going to do that? Since we already did that. How do you make terms, successive terms, change sign? -1 to the n, right? So you know that that's going to be part of it. Okay, Paris, Nathan, okay. Okay, what happened there? There we go. So now for the second one, right? When n equals 1, that an equals 2. N equals 2, an is -5, etc. So you definitely see there's got to be a -1 raised to a power in there. Now you notice how that they got that. They didn't raise -1 to the n. They raised it to the n plus 1. Well, if they would have had it raised to the n power, then the first term would have been negative. And it's positive. So they said, okay, we'll fix that. Let's make it n plus 1. You could have done n minus 1. But instead they did the n plus 1. That's fine. So this term here will start out positive, and then it'll flip sign for every term. Now the rest of it, you have to just kind of look for the pattern. If it's not something like doubling, then it's probably something about squaring or something like that. This can be, well, since we're all looking at it anyways, n squared plus 1. When you notice that, 2 is close to 1 squared, and 5 is close to 4 squared, and 10 is close to 3 squared, you kind of get the idea. It's probably involving the n squared. And it is, n squared plus 1. So the n squared plus 1 gets you the 2, 5, 10, 17. The -1 to the n plus 1 makes that sign flip from term to term and start positive, not negative. Okay, now this is a recursive. This is one of those concepts that tends to goof us up a little bit, and that's a recursive sequence. A recursive sequence, what you notice is the formula here, we're using a sub k, not a sub n, but in the end, k is essentially a counting number, so it's not a lot different. They could have used a sub n. They just generally don't when they do recursive. But what's on the other side is not an expression that has k in it. It's an expression that has previous terms in the sequence, right? If we say ak equals 2 times ak minus 1 plus 1, that means this is a general statement that a term in the sequence is defined as 2 times the previous term plus 1. Right? That's what the relative position of terms in the sequence is. If it's this one is a subscript of k and this one is k minus 1, then this one came right before this one. So you're not plugging in the value of k. You're plugging in a term in the sequence. Right? Now, usually with a recursive, they got to give you some place to start. So they do. Right here, they say if you got to like base the value on a previous term, then you got to give us a previous term. That's why it says A1 equals 3. Then for A2 will be 2 times 2 minus 1, A2 minus 1, or 2 times A1, the previous term, plus 1. Okay, so that goes here. You just plug in the previous term there and calculate, and you get 7. Now, the A3 will be 2 times A2 plus 1. Okay, well, we calculated A2 there, so plug that in there. The A4 will be 2 times A3 plus 1. Okay, that's A3, so plug that in there. And the A5, 2 times A4, means plug that in there. Oh, that was not a good arrow there. Undo, undo. It should have gone like this. So that's what recursive is. You just keep plugging in the ones before. But you know, the pattern may be different. This was 2 times the term before plus 1. But there could be other variations of the same thing. This is probably, these end up always being like the most missed questions on the test. Okay, now a kind of pretty well-known recursive sequence is called a Fibonacci sequence. And it goes like this. I mean, you could hear, I mean, I've heard Fibonacci on Jeopardy probably in the last month, you know, I mean, it comes up. Not that this specific formula, like they know what they're talking about, but they're using that guy's name, Fibonacci, who was certainly a famous Italian, because you wouldn't say that name pronounced like that except for he's from Italy. Okay, now notice that the formula here, this is a recursive formula. It's actually not just based on the previous term, it's based on previous term and 2 terms before. So a term in the sequence equals the term 2 terms before it plus the term right before it. Right? The k minus 2 tells you it's 2 before the k. The k minus 1 tells you it's 1 before the k. And so if we're going to start this, we got to be given 2 terms in the sequence. So you've got to plug in 2 terms, right? So that's why they're going to give us A0 and A1. Now, I don't remember if it said, some of you that are copying this, but you notice something different here. A0. Is 0 a counting number? technically not. You know, if you call the natural numbers the counting numbers, then 0 is not in it. But sometimes sequences start with 0. They won't be negative, but it's not uncommon to use a sub 0. Okay, so let's see. That would tell us, based on this formula, A2 should equal A0, that's the 2 before, and A1. Just take the 2 that go before. Okay, well, what are the 2 that go before? Right here. Right. So you plug in, the A0 goes here, and the A1 goes here. And you add them up, right? That was 1 plus 1, that's 2. And now if you want to find the third term in the sequence, you're going to have to add up the first and the second. Okay, well, the first we already got, right? That came from up here. And the second we just calculated. So we just plug that in here. And everyone goes the same way, right? Now, when I need the second term we already put in there, now it goes here. And the A3 goes right there. So that's kind of a famous example of a recursive formula, Fibonacci. You could notice it says write the first 6 terms. So how is it we got the first 6 terms and it ends with A5? Z. Wake up. Wake up. Because it starts with 0, right? Because it started with 0. It says first 6 terms. They gave you the first 2, so you just have to calculate the next 4. Here, Jamaica, Paris. Come on, don't go too far. That's it. So factorials. You may have already dealt with these. Factorial is represented when you take the n, again, a counting number, and you put an exclamation point after it. That's called n factorial. And what it means is, right, it's 1 times 2 times 3 times 4, all the way up till you get to that number n, whatever it is. So for example, 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. That's what we mean by factorial. Now, that leaves out, because sometimes it'll happen, that we end up with a 0 factorial. And 0 factorial, by definition, is 1. So if you end up with a 0 factorial through some simplifying process, then you're going to write 1. Just replace it with a 1. Okay, so writing the terms of a sequence when there's a factorial involved. So now here's the formula for the nth term of a sequence, a sub n, but there's a factorial in there. There's an n factorial in the denominator, and it says start with n equals 0. So here's the first, the a sub 0, since they said to start with 0, you would plug in for the exponent 2 to the 0. For the factorial, 0 factorial, right? Anything to the 0 power is 1. 0 factorial defined as 1, 1. You know, the 1 factorial, 2 factorial, 3 factorial, we already did those, right? 4 factorial would be 3 factorial times 4, which makes it 24. 6 times 4. Good, good. Okay, so simplifying factorials. That's the next one, right? Simplifying factorials, right? If you have 8 factorial over 2 factorial, 6 factorial, I mean, you could just write out all the numbers, right? That would be 1 times 2 all the way up to 8. And in the denominator, the 2 factorial is the 1 times 2. The 6 factorial is 1, 2, 3, 4, 5, 6. And then cancel common factors, right? 1 through 6 are repeated here and here. And which leaves you what? 7 times 8 divided by 1 times 2, 28. Forget why I did that. Where's my book? That's number 7. 7. Oh, because that was... That doesn't seem... Oh, it's over here. Oh, you know what? Gosh darn it. Okay. So if you have n's involved, that always confuses us, right? But just understand n factorial is 1, 2, 3, keep going until you get to n, right? What was the term right before n? N minus 1. Right? And n minus 1 factorial would have been 1 times 2 times 3 all the way up to n minus 1. So what's in common? The common factors are everything from 1 to n minus 1. So they all cancel. And the only thing left is n. Normally when you simplify these things, you don't end up writing out all these numbers like that. I mean, what I would do in this one down here, since it's 4 factorial in the numerator and 3 factorial in the denominator, I would just write it like this. I'm going to write the 4 factorial like 4 times 3 factorial. Oh, what did I do there? I made an imaginary number. 4 times 3 factorial. And then there's a 3 factorial in the denominator. And then you can cancel the 3 factorials. The same thing in the numerator, if it's n plus 1 factorial over n factorial, right? N plus 1 factorial would be n plus 1 times n factorial, right? The n factorial will take care of everything from n down to 1, and then divide that by the n factorial. Right? So 4 factorial, just split off the 4. 3 factorial takes care of the rest. Now you can cancel those. Right? N plus 1 factorial is n plus 1 times n minus 1 all the way down to 1. So just split off the n plus 1, let n factorial take care of the rest, cancel, cancel. And all that's left is 4 times n plus 1. Now, a series, or definition of a summation notation. The summation notation is this Greek letter. It's a Greek letter sigma, right? And sigma, that's a capital Greek letter, sigma. There's a lowercase sigma that comes up in stuff, sigma. But we're not using that. We're using a capital letter sigma. The summation notation has a formula, the formula of a sequence is right here. In this case, they're calling A sub I. You know, formula for the term in the sequence. Right? It's not using n, right? It's not using k. It's actually using I. But notice below the Greek letter sigma, it has I equals, and that's called the lower limit. And what we're going to do is we're going to plug in to whatever the formula is, I equals 1 to get our first term. And again, this is a summation, so we're going to add what we get if we have let I increment now to 2. So plug in I equals 2, that'll be the second term. And then you keep going. I equals 3, there's the third term. I equals 4, there's the fourth term. And you keep going until you get to whatever that number is on the top. That's called the upper limit. So it's a way to, actually I should have said, the I is the index. The lower limit is the 1 part, right? I is an index. Okay, so using the summation notation, right? If you have and please don't copy every little thing, right? The I equals the sum, right? You're going to read this. The sum from I equals 1 to 5. How many terms are we going to have if it goes from 1 to 5? 5 terms. And the formula we're going to plug into is 3 times I. So start with I equals 1, plug it in. Then go to I equals 2, plug it in. And keep going until you get to what number? The top number. So we generated 5 terms by plugging in I equals 1, 2, 3, 4, 5. And you add them up, you get 45. Yeah. Yes. Look at the next one. The counter, now they're not using I, they're using K. Okay, it doesn't matter. It could be anything, right? But K starts at 3 and it goes to 6. How many terms is that? No, it doesn't start at 1, it starts at 3. So it's not going to be 6 terms. It's 4 terms, right? It's not even 6 minus 3, right? Just like this one is not 5 minus 1, 4 terms. It's actually 1 more than you get when you subtract. So 6 minus 3 plus 1, 4 terms. That's how many you expect. And again, just use whatever is the formula and plug in 4 times. 3, 4, 5, and 6. And you can see on the last one, right, they're going from I equals 0 to I equals 8. How many terms is that going to be? 9, right? 8 minus 0 is 8 plus 1, 9 terms. And it's 1 over I factorial. And you could just see there's the 9 terms. And they actually turned them into fractions there. And they added them up and they got this number, 2.71828. And that is actually a number that we're fairly familiar with. Now, understanding that we only use 9 terms in the sequence. So it stopped at a certain point. But if you let that sequence keep going, like make that 10 or 20 or 100 or something, that's the the irrational number e, the base of the natural logarithm. And it equals, if you were to replace this 8 on the top with this symbol, what is that symbol? Infinity. Just means sometimes sequences will converge to a sum, and this one will converge to whatever that number is. If you see that, if you're not familiar with that symbol, which I think comes up on the next slide, but it's like an 8 laying down. That means infinity. So again, we talk about e being the natural base or the base of the natural logarithm. You say, well, what's natural about it? That's kind of unusual that this thing would be converging to exactly that number, or that it came up when we did our compound interest, and we had a formula for fixed number of terms in the sequence, and then we had a formula for continuous compounding, right? And it came up there too. That's what I kind of mean by natural base. It occurs in many places. Okay, there are some properties of sums. Basically, if you have the sum of, and there's an expression there that has 2 terms in it, you could split it up into 2 different summations, right? The summation of a sum is the sum of the summations. Just break it up. The same thing would happen for a subtraction. This one up here, what this is saying here is, let's say that I had I equals 1 to 10 of 4. Well, let's see. The first term I'm going to get when I plug in I equals 1. There is no I. So what's the first term? 4. It'll be 4. I mean, whatever the value of I is doesn't change the term. So the first term is 4. Okay, then you go to the second term. I equals 2. What's the value of the second term? 4. I mean, it's going to be 4 every time. It's a constant, right? And I keep doing that. How many times? From I equals 1 to 10, right? Right, that's 10 times. which means that's 10 times 4, which is 40. That's what that formula is saying. If you got a summation of a constant, then it'll just be whatever is, however many terms times that constant. The other one is, let's say that there's a constant inside the summation. I mean, it's a constant multiplying the entire expression. You could factor it out. You could just take it out. I mean, there would be no reason to say the sum of I equals 1 to 10 of 3k. I mean, if you're going to have the 3 inside, you might as well just pull it outside. Have smaller numbers when you add them up, and then multiply it all by 3. That wasn't a good, I should have used a k. The definition of a series is the sum of the first, well, I'm going to read it exactly because this gets a little tricky the way they word this stuff. But let's say we have an infinite sequence. Okay, how do you know it's infinite? The dots, right? The sum of the first n terms, meaning the sum of a finite number of the terms there, is called a finite series. So we're starting with an infinite sequence, and we're just adding up the first so many terms. That's called a finite series because it's a finite number of terms. Now, if you are adding up an infinite number of terms, which sometimes you can do, then that's called an infinite series. You know, if you're adding up the whole thing and it just keeps going, you know, you can do that kind of thing. Again, if you remember back to when you did this before, a geometric sequence was something where each term was a product is multiplied by a constant from the term before it. And if you had if the constant was less than 1, then it would look something like this. If I say I'm going to walk to the end of that board by going halfway to the end with each step, and each step is like a term in a sequence, then I go here on the first one, I go here on the next one, I go here on the next one, and I keep going halfway to the end. But do I ever get to the end? No. But what I say is that the sum is converging to whatever that point is. I'm going to get infinitely close, kind of like an asymptote. So it does make sense sometimes to say we're going to do an infinite series or an infinite sum. Doesn't always work, but it sometimes works. Okay, so finding the sum. Find A, the third partial sum, and B, the sum. I think I missed something there. Second. Okay, let me do this. Okay, so what we call the partial sum, the nth partial sum means the sum of that many terms. The third partial sum means the sum of the first 3 terms. Right? Here's the infinite sequence or infinite series that we're dealing with right here. So it just means plug in from 1 to 3 terms. And since it's so simple, right, it's 3 over 10, 3 over 100, 3 over 1,000. That's 0.3 plus 0.03 plus 0.003 0.333. Just add them up. Now, when it says the sum, that means, okay, now we're not saying just the first three. What would be the infinite sum since it said infinite? Well, what do you think would happen if I just kept adding another term? What would the next term look like after 0.003? 0.0003, and the one after that, add a 0. Keep adding a 0, and it just keeps giving you one more 3. So what number is 0.3 repeating? What fraction equals 0.3 repeating? 1/3. So that's all that is saying. So now we're doing the whole thing. Starts at 1, goes to infinity. That's your infinite part of it right there. And every one is just adding on another decimal, place filled with a 3. So that's 1/3. And compound interest, right? So if given a formula, right? If given a formula, you're asked to use it. Investor deposits $5,000 in an account that earns 3% interest, compounded quarterly. And it sounds kind of familiar to a formula we've used before, right? We had the A equals P times 1 plus R over N to the NT, right? That was compound interest. This is close, but notice the difference. They said quarterly, so there's the 4 for the N, but they don't have NT in the numerator. Remember, N was the number of compoundings per year, but in this formula, it was multiplied by the number of years. So what was NT? The total number of compoundings. And they just redefined N to be the total number of compoundings. So how would we write the first 3 terms of the sequence? What would A1 be? Plug in 1, right? Just plug in 5,000 times 1 plus 0.03 divided by 4 raised to the first. Right? How would you find the second term in the sequence? Plug in 2, okay? And the third would be N equals 3. Find the balance in the account after 10 years by computing the 40th term of the sequence. So again, A40 would just be plug in N equals 40. At that point, it just, plug it in, put it in your calculator, see what you get. Okay. So again, that was kind of basics of sequence and series, which we don't generally take a day to do that, but we have the time, and that's not your homework, because what I didn't realize is this book, even though it's based on your book, it's not exactly the pre-cal book. So let's come up with some good homework here. So make the homework. Right. The homework is on page 625. And I think we should be able to do about 1 to 5. 23, 25. That's using factorials. A recursive 29. Let's just do the 29, 31. We don't want to do that. We already did that. Let's do a 73, 70, no, 73 to 77. Let's do a find the sum. The sigma notation, just do one of those. Odds. Okay, sorry, it's a lot. Usually the first lesson of a thing, it's a lot of introductory stuff, and you have to just practice a little bit with all of it.